So, hello, our talk today is by Jane Breen. She's our postdoc here of the department who is probably grading. And she will be talking about Kemenys constant and random walks on graphs.
Yeah, so Kemenys constant has become kind of like my thing now, or at least I'm trying to make it that way. So in this talk, I'd just like to give you the idea that Kemenys constant is pretty great, it's useful, it's interesting to work with, and hopefully I'll work on it with some of you in the future. And Kemenys constant comes from Markov chains. So first I'm going to tell you about what Markov chains are. And the kind of Markov chains we're going to think about, you could just think of them as a system which occupies one of a finite number of states at any given time. And then in discrete time steps, it transitions from one state to another. And then for every pair of states that I have, there's some transition probability dictating whether, like, how likely I am to make that transition. So here from state 2 to state 1, there's a probability of 0.5 that I make that transition. And the way that I've set this up, it should be clear that such a system is memoryless. So the behavior of it in the next time step depends only on what state I'm currently in. So if I'm in state 2, I have all these different probabilities of going to different states. And then what happens next is just dictated by those probabilities. So what this means is if I take all these transition probabilities and I put them into a matrix, then that matrix represents my Markov chain entirely. So we call it T. It's a transition matrix. The ijth entry is the probability of going from state I to state j in one time step. And all the rows sum to 1. And we can have diagonal entries non-zero. This just means that I have a probability of staying in the same state in my next time step. And then everything that I might need to know about my Markov chain can then be calculated using this matrix. So for example, if I wanted to know about the long-term behavior of my Markov chain, I get this from the left eigenvector W corresponding to the eigenvalue 1, where I've normalized so that the entries sum to 1. So now the entries represent probabilities. And this represents the long-term behavior in that the ith entry of my stationary vector gives me the long-term probability that I'm in state I. So with this example here, the stationary vector is this guy down here, and looking at this right away, it's clear that state 4 is the one that I'm most likely to be in the long run, because this entry is much bigger than the others. And looking at the probabilities we've got, that's not that surprising, because if I'm in state 4, then with probability 3/4, I stay in state 4, and even if I leave, I'm quite likely to go back in. So it's not surprising that I get kind of stuck in state 4. Okay, that's the long-term behavior. For the short-term behavior, we talk about mean first passage time. So this is just the expected time it would take me to get to state j, given that I start in state I. There's a formula for that in terms of the transition matrix too, which we won't worry about in this talk. And these can range pretty widely. So if for this example, again, if I wanted to calculate the mean first passage time from state 1 to state 2, that's just 1, because with probability 1, I go to state 2 in one time step. But for the mean first passage time from state 2 to state 1, the expected time it'll take me to get back to state 1 from state 2 is 20. Because, yeah, sure, I could go back right away, or it might take me a really long time if I go to state 3 and state 4 and move around there for a while. So this is the expected time it'll take me if I just move randomly according to these probabilities. Okay, and there are two motivations that I want you to keep in mind while we're talking about Markov chains, just two applications of Markov chains. One, which is my favorite, is a road network model for that we can use a Markov chain for. So this would be where my states of this Markov chain are road segments, and then I move from one state to another. That corresponds to a vehicle driving from one road segment to another, right? And the probabilities of these can just be calculated using traffic data. If you just stick a traffic camera on a red light or something, you can calculate the probabilities that people will move from this road to that one. So you can model a road network using a Markov chain, and then in this context, the stationary vector, that represents the buildup of traffic on each road segment. And mean first passage times would just tell you the expected time to how well connected these two segments are. Now obviously people don't drive randomly, but it gives you a nice overall idea of how traffic acts in this network. The other kind of Markov chain you could think about might be one that you're more comfortable with, and that is a random walk on a graph. So this is just where if I'm on a vertex of a graph, then I choose one of my neighbors with equal probability to move to in my next time step. So the transition probability from vertex I to vertex j is just 1 over the degree of my vertex I. And I can write down my transition probability matrix, and then I've got a Markov chain. Okay? So you can keep those two in mind while we're talking about this stuff. But now I'm going to start telling you about Kemeny's constant. So Kemeny's constant, if I've got a transition matrix for a Markov chain, I've got its stationary vector, and I've got its mean first passage times. I'm going to define this thing where I fix a state I, and then I think about the expected time it'll take me to get from state I to all of my other states. And I'm going to get the kind of average of those where I'm going to weight the average by how important that state is in my chain. So it's the weighted average of my mean first passage times from the state I'm in to state j, weighted by the jth entry of my stationary vector. So this would kind of give you an idea of if I'm in state I, how is my access to other states good or bad. So you can also interpret it as the expected time it takes to reach a randomly chosen state if I'm in state I. Astonishingly, and this word is used in every paper about Kemeny's constant, that's a constant. It doesn't depend on what state you're currently in. Right? So no matter what the state is I, that's going to be equal. Okay? So that is what we call Kemeny's constant, and we denote it as k of t, because there's no need for this index I if it's a constant and it doesn't depend on I. And you can kind of wiggle around with the definition a little bit and also write it in terms of this weighted average, where rather than just fixing a state I and thinking about an expected time it takes me to get to a chosen destination state, it's just the expected length of a random trip. So I choose both my starting state and my ending state randomly. And then Kemeny's constant represents the expected length of a random trip in the Markov chain. Yeah?
Do you have a qualitative explanation of why it's a constant?
Oh, we'll get to that. I don't. And I'll get to it, yeah.
So in this has a convention that MII is 0?
No, you can calculate it's the expected time to get back to state I if okay. So, brief history of Kemeny's constant. The first place I could find anything about it was Kemeny and Snell wrote a book on finite Markov chains in 1960. And in this book they used this generalized inverse quite a bit. They called it the fundamental matrix of a Markov chain. So it's a generalized inverse of the matrix I minus t, which is a singular matrix. And so it's written like that, and then lots of things can be calculated.
Excuse me, this is not a generalized inverse in the matrix sense of a generalized inverse.
Possibly not.
It's a different kind, it's an inverse of a related matrix, because it's an
Right.
actual inverse, right?
Yes, but it acts as a generalized inverse for I minus t as well, I believe.
Ah, okay,
Yeah.
so in the matrix sense.
Yes.
Generalized inverse.
Yes.
Thank you.
So most of this book is working with this matrix Z, and lots of things can be calculated using it. For example, the matrix of mean first passage times, you can write down a formula for it in terms of Z here. So the first instance of Kemeny's constant was a corollary to some other theorem where they said let C be the sum of the diagonal entries of this fundamental matrix. And then there's this expression here, which approaches C minus 1. And the interpretation of this, without getting into their notation, is that the number of times state J is visited is the same in the long run, independent of where I started. So they just said that, and then they moved on. And one section later, then they have another theorem that says, let C be the trace of this matrix again. Then, okay, if I translate this notation, this psi here is the all ones vector. That C is our trace, M is the mean first passage matrix, and this alpha transpose is my stationary vector written in a column. So really what this is translated to is that this sum overall J is equal to, it's a constant. And they just said it, there was a 3-line proof, and they didn't comment on it at all. They just started a new section after that. So there was no discussion about what this was, what it represented, nothing. Until quite a few years later, Snell wrote a book with Grinstead called Introduction to Probability. And in chapter 11.5, exercise 19, it says, show that for an ergodic Markov chain, that this weighted average of the mean first passage times is equal to this thing, which we'll call k. Second expression above shows that the number k is independent of I. The number k is called Kemenys constant, and then this is an answer to your question. A prize was offered to the first person to give an intuitively plausible reason for the above sum to be independent of I. See also exercise 24. So if you're wondering what exercise 24 was, exercise 24 is Peter Doyle has given this following explanation for why Kemeny's constant should be a constant. Do you think he should have gotten the prize? So he was given the prize, but I think it was $50. And they mailed it to him, and it got lost in the mail. So that's the end of the story of the cash prize. And his reason was something to do with the maximum principle, and possibly was more intuitive if you were coming at it from a stat side of things, but I think not that many people are satisfied that that's an intuitive reason, I think. Okay, so I think that was kind of all really. I'm sure there was some discussion going on in the background and stuff, but not much was published on Kemeny's constant or done anything with it until these two guys, Levine and Loiseau, I don't know how to say his name, it's French, who are two computer scientists who are working on stuff like modeling the World Wide Web. And so they were talking about having a random surfer on the World Wide Web who was lost somewhere in the websites, and they wanted to know how many clicks it would take him to get to a target one. And they figured this was Kemeny's constant. And among what they did was they pointed out that if you've got this relationship with the trace of this fundamental matrix, then you can write down an expression for Kemeny's constant in terms of the eigenvalues of your transition matrix. And so I don't think that was a particularly wow theorem or anything, but once it was written down, then this allows for a lot of bounds and things to be, a lot of different computations to be done with Kemeny's constant, rather than working with the stationary vector and the mean first passage times, which are both kind of tricky to handle anyway. This gives us a much more clean way of dealing with it. So for example, using this expression, you can show that Kemeny's constant, if you've got a Markov chain on n states, Kemeny's constant will be bounded below by n minus 1 over 2. And the proof of this is pretty simple. If I think about the eigenvalues of t, 1 is an eigenvalue, and then I have lambda 2 down to lambda n. 1 is the spectral radius, so all of these are less than 1 in modulus. So if my lambda j is real, then the smallest that term can be in my sum is 1/2, if lambda j is equal to -1. And then for the complex eigenvalues I might have, well, they occur in pairs. And if I just look at those two terms in my sum, and I think about lambda j being a plus bi, lambda j bar being a minus bi, then I get this expression here, and since a squared plus b squared is my modulus and that can't be bigger than 1, I get that this is greater than or equal to 1. So if I add up all the terms in my sum, either by pairs or by individually where they're bounded below by 1/2, I get n minus 1 over 2. So that's the smallest Kemeny's constant could be. Are there any questions so far? I'll keep going. Please feel free to interrupt. Okay, so, this is my favorite part. It's all my favorite part, I like it all. So the applications of Kemeny's constant, there are a lot of them. So the first motivation I gave you for Markov chains was this road network application. And in that paper where they came up with this model for road traffic, they used Kemeny's constant to decide which roads were most important in my network. So what they did was they had this kind of toy model, and you just close a road by, taking out some transition probability, setting it to 0 and redistributing the probability somehow. And then calculating Kemeny's constant each time for this. So if I close this one, Kemeny's constant has a certain value. If I close this one, I get a different chain with a different Kemeny's constant. And so using this, the ones that make Kemeny's constant much higher, so poorly connected, those are important roads in my network. That's what they said. Another application is in robotic surveillance, which sounds cool. And there were a group of engineers who wanted some classical problem of finding an intruder in a network and coming up with an algorithm to give your robot to be able to discover the intruder. And so what they did was they have some semi-definite program that determines the best transition probabilities that would minimize Kemeny's constant in this network. And so they just tell their robot to use those transition probabilities. And this algorithm that they came up with outperforms a lot of the state of the art in that field, which I think is pretty cool. Globalization of the economy. This is one where similar to the road networks one, because they use some of the same ideas. They take all this data from the world input-output tables that say something about how much different economies contribute to each other. So different economies, like in, I don't know, car manufacturing in different regions and how this one contributes to that one, or within the same region and that kind of thing. So they came up with a Markov chain model for that, and then they had one for every year. So these world input-output tables, they update every year, I guess. And so they showed that Kemeny's constant, if you measure Kemeny's constant for each of these chains, it's decreasing over time, which means that our economy is becoming more globally connected. Complex networks is also a place where it's being used, so things like protein interaction networks and things like that, or the World Wide Web. And then the last one is not really a real world applications, but I guess through the lens of spectral graph theory, there are other real world applications that we get for Kemeny's constant. Okay, so the connection with spectral graph theory, that's the next thing we'll talk about. So most of you will be familiar with the normalized Laplacian of a graph, I think. So if you have a graph, a connected graph on n vertices with degrees d1 down to dn, and your adjacency matrix and your diagonal degree matrix, the normalized Laplacian matrix is defined like this. This only works if it hasn't got any isolated vertices. But the ij entry is minus 1 over the square root of the degree of the ith vertex times the degree of the jth vertex. If there's a connection between them, there's ones on the diagonal and everything else is 0. So there's a connection between this guy and Markov chains in that if I take this similarity transformation of my normalized Laplacian and look at what it does, well, d to the negative 1/2 times d to the negative 1/2 is d inverse. And here I'll get the identity. So it's d inverse times d minus a, which is I minus d inverse times a. Right? So d inverse times a is the transition matrix for the random walk on the graph, right? Because the transition probability is 1 over the degree of my vertex coming out of that. So what that means is my normalized Laplacian is similar to this guy, which means that it's cospectral to that guy. So my eigenvalues of my normalized Laplacian, I have mu as an eigenvalue of L, if and only if 1 minus mu is an eigenvalue of my transition matrix for the random walk. So what this means is that rather than write Kemeny's constant for the random walk on a graph in terms of eigenvalues for the transition matrix, I can actually write them down in terms of eigenvalues for the normalized Laplacian. So there's this lovely connection with spectral graph theory. And there's not been a lot done with this yet. I'm quite excited about doing some stuff with this. This is going to be the subject of the undergraduate research project we're going to do in the spring, myself and Kate and Steve, but there's lots of things you could do with this, so I'm excited to see what would happen there. Okay, so given that there's this connection with spectral graph theory, let's talk a little bit about how Kemeny's constant can be written down in terms of combinatorial stuff. So, a lot of you might be familiar with Kirchhoff's matrix tree theorem, which says that if you get the regular Laplacian of a graph, and you take some cofactor of that, that's the number of spanning trees of your graph. So there's this connection between spanning trees and determinants, okay? Now, there's a generalization of that called the all minors matrix tree theorem, which I won't get into in any detail at all. But with that, and with this result here, where Kemeny's constant is written in terms of these determinants, using some stuff about the characteristic polynomial, what we get is a theorem about that can give us Kemeny's constant in terms of a bunch of different types of spanning trees of the graph. So this is long, and you have to bear with me through through defining all of the terms, right? So let's say we have a simple undirected graph, and we're thinking about the random walk on the graph. I have the degree vector for the graph, that's fine. M is the number of edges in my graph. Tau is the number of spanning trees of my graph. And then this guy, so for any I and j, I'm going to let sigma ij be the number of spanning forests I could have of my graph that consist of exactly 2 trees, one of which contains vertex I and one of which contains vertex j. Okay, that's what sigma ij is. Right, with all of those things defined, Kemeny's constant is this thingy here, where this sigma is the matrix of all those sigma ij's. So we've got this kind of weighted sum of these sigma ij's, where we weight it in terms of the degrees of the vertices. Okay, that seems kind of complicated to work with, like a little bit nasty. So what if we thought about, rather than thinking about random walks on graphs, what if we just looked at nice graphs like trees and see how this simplifies? So if I have a random walk on a tree, the number of edges is going to be n minus 1. How many spanning trees am I going to have of my graph? 1, right? And then can anybody think of how I could write down what sigma ij would be? So if I have some tree and I pick a vertex I and a vertex j, how many spanning forests am I going to have consisting of 2 trees, one containing vi and one containing vj?
The distance between?
Yes, because there's the distance between them, that gives me the number of ways I could split them up. Yeah. So in that case, if I'm just thinking about random walks on trees, then it boils down to this. I need the degree vector, I need the distance between vi and vj for each I and j, and then I get this expression here for Kemeny's constant. And so that, in and of itself, was quite a strong result, because what the authors of that paper were able to show is that this means that almost all trees have a brace edge, where a brace edge is when, if I've got a tree and I've calculated Kemeny's constant for the random walk, there's an edge I can add that causes Kemeny's constant to increase. So my thing is somehow less connected, even though I've put in another edge. So that was kind of a nice, surprising result. And I hope convinces you more that Kemeny's constant is like, interesting. Okay, so the last thing that I'll talk about is the most recent stuff I've been doing with Kemeny's constant. And I can't stand here and tell you how useful Kemeny's constant is and how interesting it is without giving some indication of how difficult it is to work with numerically. So I gave a bunch of examples where people were using this in applications, but Kemeny's constant is no good to them if every time I try to calculate it, I get something that might be off by quite a lot. So this is what conditioning is. We're going to talk about conditioning. And a condition number is something, it measures how sensitive the output of a function is to perturbations in the input. So the idea is that if I'm working with, like, I want to get my transition matrix T and I want to calculate Kemeny's constant for it. But whenever I put my transition matrix T into whatever software I'm using, it's not really the real transition matrix. Like, either I've had to truncate some of the data so that I've got like less decimal places than I should, or maybe I'm just estimating stuff from data and it's not really the true value of what it would be in the population. So I want to know is, if I'm calculating it for this thing that's off by a little bit, how bad is my Kemeny's constant going to do from there? Like, if there's just a small error here causes a big error in Kemeny's constant, then that's bad. And I need to know how much that's going to happen. And so you might have seen this before in solving a linear system. So if you have ax equals b and you're trying to solve for x here, the condition number for that matrix A is the largest singular value over the smallest singular value. And that tells you how well conditioned or how poorly conditioned your matrix is. In Markov chain theory, traditionally what's happened is we've done it for stationary vectors. So if you've got your transition matrix and you perturb it, so you get t tilde, which is t plus some error, where you kind of add some and subtract some off certain things. So that the rows of E are going to sum to 0. Then you're going to have W, the stationary vector of t, and W tilde be like the one that you've actually calculated. Then there's all kinds of, like a condition number is usually of the form where the norm of W minus W tilde is bounded by some function of my transition matrix multiplied by the size of my error. And some ones that are known are, one condition number is the infinity norm of that fundamental matrix. Another one is written in terms of the mean first passage times. And so you kind of get some relationships between, like, if I have some very large mean first passage times, then my stationary vector is going to be poorly conditioned and things like that. Okay. Oh, I completely by the by. Kemeny's constant is a condition number for the stationary vector. So nothing to do with the behavior of Kemeny's constant at all. And I think this was even kind of written down before people started working with Kemeny's constant as a thing in and of itself. That if I have large values for Kemeny's constant, that can also mean that I've got a very poor, like I could have a lot of error in my stationary vector. Okay, but the natural question to ask is, if I perturb my matrix T to get T plus E, can I find some function of my matrix that will bound the error in my Kemeny's constant relative to the size of my error, matrix E? And so, well, one of the tools we're going to use for this is a different generalized inverse called the group inverse. So I'm going to let Q be I minus T, the identity minus the transition matrix. That's a singular matrix because it has an eigenvalue 0. Then Q sharp is what we use to denote the group inverse. And it's a type of generalized inverse like the fundamental matrix Z is, but it's a little bit nicer to work with, in my opinion. And so the eigenvalues of Q, which are just I minus T, they're 0, 1 minus lambda 2 down to 1 minus lambda n. And the eigenvalues of Q sharp are 0, and then all the non-zero ones just get inverted. So the Kemeny's constant for my transition matrix is just the trace of my group inverse Q sharp. Okay, so what I want, right, I'm going to perturb my transition.
Sorry, is
Yes.
it obvious? Kemeny constant is just a trace?
Yeah, so it's the eigenvalues of Q sharp are these guys here, and that was just the definition of Kemeny's constant. Yeah. Okay, so I'm going to have, this is all my notation. I have T, which is my transition matrix. I perturb T to get T tilde. Q is I minus T, and then Q tilde is going to be the group inverse of my perturbed guy. So the question is there an expression for Q sharp tilde in terms of the other ones? Because if the trace of this and compare it with the trace of Q sharp. And so the answer is yes, that I minus E times Q sharp is invertible, and Q sharp tilde is that guy. Okay, so I just need to get the trace of that, and then I've got my perturbed Kemeny's constant. Okay, but so the nice thing is, right, I'll tell you in advance so that you're not scared off the next few slides, that the trace is additive, right? So it's the trace of this minus the trace of this thing, and the trace of this thing is 0. So I'm only going to be left with the trace of this thingy. So it's at least a little bit better. Okay. Right, so the first thing we'll do is write an expression for Kemenys of my perturbed guy in terms of the last one is just this infinite sum of these like increasing powers of Q sharp. So the proof of it is just, so as I said before, the trace of that larger other term was just 0. So I'm just thinking about the trace of this one. And then you might remember from a matrix analysis course that if the spectral radius of a matrix is less than 1, then you can write the inverse of I minus A as this geometric series, right? And so here, if the norm of E is sufficiently small, then the spectral radius of E times Q sharp is going to be less than 1. And so I can write it as this sum, and then just multiplying through by Q sharp and taking the trace, I get trace of Q sharp plus trace of Q sharp EQ sharp plus, and then we've got all these extra terms. All right. So I've got this expression for the difference between my perturbed Kemenys and my original Kemenys. And there's, like, this is the dominating term, this guy here. Now, that stuff is like, there's a lot of it there. So one thing we'll say is that, well, the trace works cyclically on products. So trace of Q sharp E Q sharp, I can also just think of Q sharp squared times E. And, like, I'll say that the difference is, if your norm of E is small enough, you can say that the difference is just kind of dictated by this guy, plus big O of these higher order terms. But what we're talking about here when we're talking about conditioning is being as precise as we can, right? I can't just flub off this, or at least I'm uncomfortable doing that. So instead we'll define a structured condition number. So this is where we take a limit, we kind of mod out by the size of the error, and then we take the limit supremum of, like, the worst I could have in the worst change I could have, where I'm assuming that the size of the perturbation is vanishingly small. Okay, so it's kind of a measure of the biggest change I could have in Kemeny's constant, where I'm assuming that my norm is small, which is still pretty good in practice. Like, in practice, this gives us a reasonable amount of information to work with. Oh, sorry, I should have warned you before this slide. Okay, so here's the result. Here's our condition number. It's that thing. So these are all entries of Q sharp squared, and then there's all these other guys where we take mins and maxes. And it's not nice to look at, but it is accurate. So if you were working with this in practice, you could just, write a program that's gonna calculate this, and that would give you the structured condition number for Kemeny's constant. Okay, but it's not that helpful for us when we're trying to get an idea of what it means for Kemeny's constant to be poorly conditioned and that kind of thing. Like, it doesn't give us a feel for what's going on in my Markov chain that's making Kemeny's constant bad somehow. So what we'll do is we'll get an upper bound, which is much nicer. So we were able to get an upper bound for our structured condition number in terms of these two known condition numbers for the stationary vector. So there are these two other guys that if they're large, then the stationary vector is poorly conditioned. And so having this connection between these means that if my stationary vector is poorly conditioned, that means that there's the potential for Kemeny's constant to be poorly conditioned. And the next question you would ask after this, if I've got this big upper bound, does it ever come close to equal here? Like, do I have some really, really bad behaving matrices that give me something close to this? And the answer is yes. So this is, it's a directed cycle. You could also think of it as like a Markov chain, which is a random walk through a directed cycle, or just you've got n states and you just cyclically go through them, right? This is actually the guy that gets you the minimum value for Kemeny's constant, that n minus 1 over 2. But this is also very poorly conditioned. So that's what the transition matrix looks like. That's what Q sharp looks like. And I don't think I've put Q sharp squared on there because it was not very nice. So I skipped right to the end where I find all these values. And it turns out for n being large enough, the structured condition number for that guy is roughly half of our upper bound. So this upper bound is pretty good in that there are some matrices that get close to it. And then another guy would be a random walk on a path, where I wasn't able to calculate what the structured condition number for this would be in general in terms of n. But what I have got is, this is the ratio of the structured condition number to the upper bound calculated for all random walks on paths up to 1,000 vertices. So you can see that it's roughly on the right order, like off by a constant or something, but it's on the right order. And both of these are of order n to the 4. So this graph, I think, was me trying to figure out what order the upper bound was. So this is I modded both of them out by n to the 4, and they roughly approached a constant thingy. So they're both on the order of n to the 4. So that's a huge change in Kemeny's constant, even though it's like, it's based on a small perturbation, and it's like multiplied by that small norm. Okay, and so, right, let's ask why these are poorly conditioned. Okay, so these two both give me bad behavior in that they get close to the upper bound. And the reason is that the matrix E that gives me the worst possible perturbation, that gives me this big gap between Kemeny's constant of t tilde and Kemeny's constant of t, it adds in all of these edges, right? It's kind of like small probabilities that when I'm here, rather than definitely going here, I could jump across. Right, so it kind of completely breaks the structure of my Markov chain and kind of destroys that thing that's giving it small Kemeny's constant. So that's all I'll torture you with for now. I'll take any questions. Yeah.
Do you think you could possibly bound the condition number based on Kemeny's constant itself?
Yes. So if you have, wait, what exactly is it that you mean?
So you have this C of t is less than or equal to n times C1 times C2, rather than, so the examples you give a very low Kemeny's constant.
Right.
Which I would tend to think would produce a big condition number by itself. So if you had, maybe making this trade-off, where if the Kemeny's constant is small, then the condition number is large, and if the Kemeny constant is large, then maybe it's better conditioned.
Well, what we can do is we can get a relative condition number in that, so this here is a measure of the difference between Kemeny tilde and Kemenys. One of these guys, I can't remember which one. I think it might be this one. This one is bounded above by Kemeny's constant, so you could just replace that in the upper bound and then divide out. And then you've got a relative bound, which is really nice as well.
Yeah.
More question?
Yeah.
Do people ever condition their definition of condition number to only allow perturbation on the support?
Yeah, and that's what we've done.
Because it seems
here.
unrealistic to, I know they did that for PageRank and all that sort of things.
Yeah. Yeah, so usually, in fact, I think, I looked it up recently because I wasn't sure why we called this a structured condition, oh, it's gone now. The structured condition number, I wasn't sure why we used that word. And a structured condition number actually more generally means where you preserve some of the structure. So what we're doing here is we're making sure it stays non-negative and stochastic, because otherwise it doesn't make sense to calculate Kemeny's constant for it. Now maybe that's not as directly applicable then to, oh, I've got some errors. It's more applicable to the situation where I'm measuring things from data, so I don't have true values, I have estimated values, and it tells me how far off I am from there.
I mean, if you just take a graph, you know where there's a non-zero value in the transition matrix, just by asking whether there's an edge there or not. So it's like the error from doing a matrix multiplication or something like that.
Yeah.
It's only going to be reflected on those places where there was an edge already.
Sorry, so you're asking if we don't allow that thing where I can get lots of extra edges, is that right?
Right.
Yeah, so yeah, we thought of that, but there are actually examples of directed graphs where you can put any, so a zero pattern for your matrix basically, where you can make the non-zero things anything within the restriction of it being stochastic, and Kemeny's constant is actually constant over the class of that. It's a very particular class of directed graphs, but so there would be situations that you'd have a non-zero pattern where no matter what perturbation you make within that structure, you don't get any change in Kemeny's constant. So then, yeah, that makes it harder to work with that problem, because you know that these exist. Yeah, that's a good question. Yeah.
So your transition matrix has fixed probabilities, but is there any like idea of this where the probabilities are allowed to change, and is there a Kemeny's constant for that case, or?
Like where they change over time?
Yeah, like from, you know, state I to state I plus one, now the probabilities might have changed. Or is that just too much?
I think, yeah, so if you're talking about like non-homogeneous Markov chains where over time the probabilities become something different,
Yeah.
those are really hard to work with. Like to the extent that it's hard to even figure out if they're gonna approach some long-term behavior nicely. So I don't think there's anything like it for that, but that might be interesting. Yeah.
Alex, are you thinking maybe that the entries would be independent random variables from some distribution?
Right,
As opposed to
right.
a fixed constant?
Mm.
That wouldn't have any stochastic implications, it would just be a random variable.
Don't know.
More questions? Okay, let's send Jane again.